some of the topics that were in your review packet. Now, once again, that review packet is required for you to turn in the day of the exam if you are taking my exam. It is not required at all if you are not taking my exam. All right? So we're going to start with some graphs and some higher degree polynomial functions. Okay, I'm going to do the first one with you, and this is, so if you haven't done the first one, let's do it together. We're going to talk about factoring. So this is the function. Okay, so to factor this, we take out the x squared. We're going to factor by grouping. We'll take out the negative 4. And so that gives us x minus 5 times x squared minus 4. And it'd be nice if we were done, but we're not done. Because the second factor, x squared minus 4, factors further. It factors to x plus 2 times x minus 2. Okay, once we have the complete linear factorization, we have factored everything as far as we can, then we can find our x-intercepts. So the x-intercepts are the zeros of the graph. So when we go to graph this, we have an x-intercept at 5, at negative 2, and at 2. Those are the values that when we plug them in, they make that product 0. So we have 1 at 5, 1, 2, 3, 4, 5. 1 at negative 2, and 1 at positive 2. Now each one of these factors is raised to the understood first power. If it is an odd power, it is going to pass through. If it is an even power, it will be tangent or bounce at that point. Well, all of these are odd, so it's going to pass, pass, pass. Now the other thing that we need to know in order to be able to graph is the end behavior. Because this is an odd degree function with a positive leading coefficient, we know it falls to the left and rises to the right. So it's going to fall, it's going to rise, it's going to pass, pass, pass. Okay? And then it also talks about the degree of the function. If it's in standard form, the degree of the function is the highest exponent. If it's in factored form, the degree of the function is the sum of the exponents. So 1 plus 1 plus 1 is 3. The degree of this function is 3. Or if we look right here, the degree of this function is 3. In behavior, as x approaches negative infinity, the function approaches negative infinity. As x approaches positive infinity, the function approaches positive infinity. Okay, I am going to post the solutions today. So as you're working through this, if you're not sure, if you need to, shake cobwebs out or whatever, look up the key. Check the key on everything you've done before you get in here Monday so that you can ask questions.
It's on the calendar.
It will be, where do you want me to post it? You want me to just post it on the main page? I'll put it on the main page for Algebra 2 in Willoughby World. Okay. All right. So that's one way. What if we had one that was already factored? Those are actually easier. If we have one that's factored and we're trying to graph it, what we would do, we would plot our x-intercepts, which are the zeros of the function. So we have one, what would make this factor 0? Positive 1. Got one there. What would make this factor 0? Negative 3. We have one there. What would make this factor 0? Positive 4. We need one there. Okay? The degree of this function is 2, oh, hold on. I didn't mean to mark it out. I meant to go here. 2, 3, 4. It's even. So it's either going to rise, rise, because an even degree function has the same end behavior, or it's going to fall, fall. This function has the negative out in front, which tells us that this one will fall, fall. It's going to fall to the left and fall to the right. At -3, it was to an odd power, so it's going to pass. At +1, it was to an even power, so it's going to bounce. And at +4, it was to an odd power, so it's going to pass. So pass when it's odd, bounce when it's even. Now, what if this one had been 3? Right here at +4, it'll still pass, but it passes with an inflection. It's got a squiggle.
Wait, what did you say about this?
The squiggle is when we have an odd power greater than 1. Odd power greater than 1. Did that help with the graphs?
Wait,
What?
so what about the x minus 1? Would that be a squiggle?
This one is an even power.
Oh, no.
So an even power bounces. So that's going to bounce. And we call that tangent because it hits and bounces back. It just touches at that point.
What number is that?
That was a made up example. Okay, so that helps you with like 1 through 4. Okay, the next section was where we started looking at imaginary. Now, we defined the imaginary unit I, it is defined as the square root of -1. So whenever we see the square root of -1, we replace it with I. And we also studied powers of I. So we said I to the first is just I squared is -1, I cubed is -I, and I to the fourth is 1. Remember the thing? I won. Okay? And the 2 in the middle are negative. So that helps us remember. It's our mnemonic. Okay, so whenever we have something like the square root of -36, well, that is just like 36 times -1. And the square root of 36 is 6, and the square root of -1 is I. Or if we had to simplify the square root of -40, that is 4 times -1 times 10. So 40 was not a perfect square, so we had to think of the largest perfect square that is a factor of 40. So this is 2I root 10. Okay? Now, sometimes we have something out in front. Like we might have a 3 out in front. So if we had a 3 and we had -12, we would break -12 up into 4 times -1 times 3. And the 4 comes out and brings a 2. And the -1 comes out and brings an I. So it's 6I root 3. So we just have to multiply by what's out in front of the radical. Are we good?
Can we do another one of the
Sure. Let's say we had 2I root -50. Okay, so -50 will break down into the largest perfect square that divides into 50, which is 25. But because it's negative, we have a -1, and 25 times 2 makes 50. So the square root of 25 is 5, and the square root of -1 is I. So we can bring out a 5 and an I. So the only thing left under the radical is a 2, root 2. But we have a 5I and a 2I. So 5I times 2I is 10I squared. But what is the value of I squared? -1. So where there's an I squared, we can replace it with -1. So 10 times -1 is -10. So it simplifies to -10 root 2. Was that your question?
Mm-hmm.
Yes, Lily?
What about like add and put equal?
Let's do one. So what do we do if we have I to a really big power, like maybe I to the 34th power? Well, this is where we looked at this pattern and we said, okay, this pattern repeats every 4. Because if we did I to 5th, we'd go back to I. I to 6th would be -1. So what we do is we take that exponent, divide it by 4, and what we care about is the remainder. So we divide that by 4 and we get 8, and the remainder is 2, which means it's the same as I squared. And I squared is -1. So it's the remainder we're looking at for the larger powers. Okay, we also worked with complex numbers, and complex have a real part and an imaginary part. We always said write your answer in A plus BI form because A represented the real part of the complex number, and this represented the imaginary part of the complex number. Now, the nice thing about this is when we're adding or subtracting complex numbers, it's pretty simple. It's just like their variables. So the real parts get added together, and the imaginary parts get added together. So that would just be minus I, and that's all we have to do. Real with real, imaginary with imaginary. So addition and subtraction kind of work the same way. Now multiplication. Let's say we have 4 plus I times 3 minus 2I. Apparently I like 3 minus 2I. We're just going to distribute here. So we get 4 times 3 is 12. 4 times -2I is -8I. I times 3 is 3I. I times -2I is -2I squared. But I squared is the same as -1. So what that does is it changes its sign. It's the bells. So it's 14 minus 5I. Okay, and then division. We can't have an imaginary part in the denominator, so if that's all we have is imaginary, we multiply the top and bottom by -I. And that gives us -5I over -2I squared. Cancels, cancels. -5I over 2. Done. So if it's just imaginary, all you have to do is multiply the numerator and denominator by -I over -I. But if it's complex, let's say we have 3 over 5 minus I. Instead of multiplying by -I, which won't get rid of the imaginary part in the denominator, we have to multiply by what's called the conjugate. The conjugate of this complex number is 5 plus I. Remember, you just changed the sign of the imaginary part. And the reason we do that is because it eliminates the imaginary part when we distribute. So we get 25 plus 5I minus 5I minus I squared. And remember, I squared is really -1. Try to change colors. So minus the negative is going to make a big old plus. So now my denominator is just 26. So when I multiply by the conjugate, it eliminates any imaginary part from the denominator, which is my goal. So these will probably be broken up on your multiple choices. Yes, ma'am.
Where'd you get the 15 from?
The 15 came from distributing the 3 in the numerator. All right, is that good for the imaginaries? Okay, roots. Okay, the next one, this is what, number 22 in your section 1 of your review packet. It says determine if 2 is a root of the function. One way to determine if a number is a root is to do synthetic division. And what will our remainder be if it's a root?
0.
0. That's right. So our function is x to the 4th f of x equals x to the 4th plus 3x squared minus 28. This is a great one to review because if we're missing a degree, what do we have to put in its place? 0. So we do coefficients. 1, 0, 3, 0, negative 28. Okay, and you always bring down the first one. Then we multiply, and we add. And we multiply. That's not 6. That's 4. And we add. And we multiply, and we add. And we multiply, and we add. So this last one is always my remainder. Well, if the remainder is 0, then my divisor is a root. So 2 is a root. And how do I know that? The remainder is 0. Another way we could do that, do y'all remember the remainder theorem? Which said if you evaluate f of 2, and we get out 0, it is a root. So 2 to the 4th, 2, 4, 8, 16, plus 3 times 2 squared. 3 times 4 is 12. Do you see I get out 0? That's the other way to do it. So we could show the synthetic, we could do the synthetic division, or we could use the remainder theorem and get 0. And if there's no remainder, it is a factor. It is a root. All right. Now, if I ask you to find all the possible rational roots, that is where we do all the factors of the constant divided by all the factors of the leading coefficient. P's and Q's. Do y'all remember the P's and the Q's? So if we had 2x squared, let's do 2x to the 3rd, plus 5x minus 12. And I ask you to list all the possible rational roots. Doesn't mean it is a root, but it's a possible. It would be all the factors of 12 plus or minus 1, 2, 3, 4, 6, and 12. All those divided by all the factors of 2, 1, and 2. So dividing by 1 doesn't change anything. But dividing by 2 does. 1 divided by 2 is 1/2. 2 divided by 2 is 1. It's already listed. 3 divided by 2 is 3/2. 4 divided by 2 is 2. It's already listed. 6 divided by 2 is 3. It's already listed. 12 divided by 2 is 6. It's already listed. So that's all the possible rational roots. So you do all your factors of your constant divided by all the factors of the leading coefficient. Okay, now, how do we figure out which ones actually are? We use our calculator. And wherever it crosses the x-axis, that is a root. Those are our roots. So we looked at our tables. Do you guys remember looking at our tables to find which ones? And the y value is going to be 0. Okay? So use those calculators. You get to. Use them. All right? Don't make it harder. Make it easier. And so let's do one like 25a. 25a is x squared. No, it's x to the fourth minus 5x cubed minus x squared plus 11x plus 6 equals 0. Now, we could list all the possible rational roots, but let's look at the calculator. And if you look at the calculator, you'll see it crosses at 2 and at negative 1. And then it crosses 2 more times, but it's not pretty. It's not an integer. So, we would do synthetic division with 2, 1, negative 5, negative 1, 11, 6. And then do synthetic division with negative 1 with this answer.
We would put that into our calculator, right?
This you can't. Okay, this you would put into your calculator and look at the graph. Yes.
Find the points.
And from the graph, you would see it crosses at an x value of 2 and an x value of negative 1. So then you got to do synthetic division. So we bring it down, we multiply, we add. We multiply, we add. We multiply, we add. We multiply, yay! We better get 0 because we know it's a root. Okay, then we do it again. Now we do it with the next one. Negative 1. Do not start over. You got to use this answer. So we bring it down, we multiply, we add. We multiply, we add. We multiply, we add. Yay, we get 0. So now we're left with a quadratic, because remember we just go backwards. No x, x to the first, x squared. So this is x squared minus 4x minus 3. Man, if this were a plus 3, it would factor and life would be good, but it's not. So we have to use quadratic formula. And you're welcome to go listen to my rap again.
Yeah.
But it's negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So we get 4 plus or minus 16 plus 12 is 28 over 2. 28, write it down. 4 and 7. The square root of 4 is 2. And then when we divide by 2, if we divide, it has to divide into everything. And it does. 2 goes into 4 2 times. 2 goes into 7. 2 goes into 2 1 time. So those are my other 2. 2 plus square root of 7, 2 minus square root of 7.
Do you always keep the number in the square root the same? Like if it was like 4 something, do you change these?
I'm not sure. Write down what you're saying and I'll take a look at it. Huh? Okay, what if this was a negative 28? What would be the only difference? There would be an I right there. Okay, now what happens if I give you the roots? If I tell you that the roots of a function are negative 2 and 3i. So this, now we gotta go backwards and write it as the factors. But if 3i is a factor, or is a root, what also is a root? Negative 3i. So when we put them back in, it's x minus this, which makes a plus, x minus that, and x minus this, which makes a plus. Now remember, we always start with opposites. If we have opposites, we start with x. So, distribute x squared plus 3i x minus 3i x minus 9i squared. But the I squared cancels, leaves me x plus 9, because these also cancel, times an x plus 2, distribute x cubed plus 2x squared, that's not an x, plus 9x plus 18, yay!
So that's for 2A through D.
Yes.
Can we go for number 4?
The clay sculpture?
Yeah.
Alright. Number 4 says we're making a clay sculpture that is a rectangular prism. We are very creative, guys, because a rectangular prism means we're taking the clay and we're forming that.
A brick?
It's like a brick. Yes. Yes, we're creative. Alright. So it says we want the height of our sculpture to be 3 inches less than the width of the base, and the length to be 4 inches less than the width. So we'll call this the width. We want the height to be 3 inches less, and we want the length to be 4 inches less. Guys, whenever you sit to do clay sculptures, do you ever make a rectangular prism?
No.
And as you make the rectangular prism, do you think of the length, height, and width in terms
All the
of its
time.
relationship?
Yes, because we usually have to make more bricks, so we have to make them equal to each other.
Okay, okay. Well, I'm so glad y'all do. All right. So, volume. All we do is multiply these three. This times this times this. All right. Now, so that's our first one. And then the second one asks for what are the dimensions of the box is 84 cubic. So we set 84 equal to this. So what would we do? We would take the lazy man's way, and we would, on our calculator, punch in this. And we would look to see what the x-intercepts are, because our x-intercepts are our answers. Okay? And the only positive x-intercept I get is 7. And I could ignore the negative ones, because can a length or any dimension ever be negative? No. So I look for my x-intercepts. The only positive one is 7. So the width is 7, which would tell me that the length is 3 less than, that the height, that's the length, and the height is 3 less than that. And this was inches. Look at me all forgetting my units. Okay. That's kind of all I feel like doing today. But that gets you a good start. We can do some more on Monday. Definitely bring me questions on Monday.
I will.
I would like to answer your mathematical questions.